All right, good afternoon, everyone. My name is Nick Valentino. I'm an academic counselor in the Hagen School. Today we are having our sixth edition of the Full Spectrum series. If you wanted to access any of the previous videos, they're all on our Facebook page, the Hagen Facebook page, which you can access. And there will be there's 5 additional ones that we have, and we're going to have 4 more coming up in the next few weeks. Next week, we'll be having electrical and computer engineering with Professor Marvin Doyley. And on Friday, we will have the Gergen Institute for Data Science with Dr. Ajay Anand. So we're excited about these coming up. Thank you for all your feedback that you have given about these sessions. We're hoping to continue these in a different form, hopefully over the break. And today we have Dr. Thomas Brown from the Institute of Optics. Dr. Brown has made this presentation for the Early Connections opportunity in the past, and we're very happy that he is here to be able to do this. So, Dr. Brown, I'm going to turn this over to you. Sorry, it was quick housekeeping. Sorry, it's Friday. We are also going to have some information from the Gwen Green Career Center afterwards. And if you're interested in winning a prize, you can put your email in the chat and send it to me, and I can respond to you to see if we can get you a prize for watching this, both if you're watching now or if you're watching it as a recording. All right, Dr. Brown, now I'm ready to turn it over. Sorry about that.
Okay, very good. All right, are you able to see this? Can you see my screen?
Yep.
And can everybody hear me okay?
Yep.
Yep.
So my name is Tom Brown. I'm on the faculty of the Institute of Optics, which is, as you have been told, is one of the departments within the Hagen School of Engineering and Applied Sciences. And so it's great for those of you who are here live, but as well as those of you who might be listening to this on a recording. It's nice to have you here. For those who are live, if you have questions, Nick is going to be monitoring the chat line. For those of you who might later on be listening to this in recording, we can't, of course, do the chat live, but you're welcome to contact Nick to get my email or send your questions that way, and he can forward the questions to me if you have additional questions. The other person that we have here that is great at answering questions about the optics program is Dustin Newman. He's our optics undergraduate coordinator, and he's a great resource for anybody that is thinking about possibly majoring or even taking some courses in optics. I'm starting out with a picture from some years ago now, February 2013, of the Mars rover Curiosity. That was one of these robotic things that landed on Mars and went all over the place. And one of the reasons why we like to show this is that it illustrates where some of the technology that optics and optics graduates go. We had optics companies that have been started by our graduates that were building components for the Mars rover, other graduates of the Institute of Optics who work at NASA on projects like this or on space telescope projects and so forth. I also like to show this. This is a picture back from 2012. It's actually a picture of the sun taken through one of Professor Zavislin's solar telescopes. And it's a picture of Venus going over the sun. But what I found really fun and interesting is that this image was recorded with just an iPhone camera, mated up to a solar telescope. And it goes to illustrate what a high quality imaging system each of us is carrying around in our pocket these days and the kind of things that we can do with it. And optics is light. It's all the technology associated with light. It's the imaging, it's the sensing, it's the generation of light. So we're going to talk to you about optics. Those of you who are in town know our campus already. Those of you who are connecting from out of town might not know this is an aerial view of the River campus. And the Institute of Optics, along with the engineering buildings, is down in sort of the lower right corner. This is a picture of Gergen Hall on the right, sort of wrapping around the Wilmot building on the left, and this is the campus home for the Institute of Optics, a pretty picture taken at night, and something I hope many of you will get a chance to enjoy. What is optics? Optics is everything to do with light, but one of the things I hope you'll take away from optics is that the world of optics goes all the way back to the ancient Greeks, fascination both with the idea of light and how to use it. This is an illustration of a story that we think might have happened, where people figured out how to polish concave surfaces and focus sunlight, and perhaps even use that to light the invading ships on fire. So those of you who have used focusing devices, perhaps a magnifying glass to light a leaf or something on fire, you're in good company. It's been around for a long time. But these days, the things we like to light up are not necessarily with sunlight, although I'll talk about solar energy. More often, we're taking high-powered lasers and we're focusing them down on different things to change materials, to sometimes change the properties of the light itself, sometimes to study the quantum mechanics of light. And so what is optics? It's the study of light. It's generation, how you produce it, it's propagation, it's detection and interaction with matter. We sort of intellectually divide this up into three areas. There's the area of quantum optics, which is you might think of as the more physicsy side of optics, but these days there's a lot of quantum optical engineering going on. But this is the idea of taking the particle properties of light, and especially some of the weird particle properties of light, and working with those. Physical optics takes light as a wave. It's the wave picture, and we use the wave-like models of light. Geometrical optics is the pictures of light as rays, and how we can use that in sometimes very, very precise optical design, and the design of very complex lens-based and other optical systems. But beyond the intellectual division, there's all kinds of fields of research. There's optical design, there are lasers, fiber optics, and we'll talk about a few of those. There's nanophotonics, how light works when it's on a very, very small scale. There's things you may be familiar with, solar energy. There is new fabrication methods. How do you come up with new mechanical and chemical processes, and sometimes even magnetic processes, to polish better lenses, fabricate new kinds of optical surfaces? How do you come up with new optical materials and better understand them? And then there's the whole world of biomedical optics. How can optics help diagnose, heal disease, and so forth? If you look around you, sometimes there are obvious places where optics is used. There's consumer photography. We're carrying it around in our pocket. We're taking videos all the time. Of course, there's binoculars, webcams, and so forth. Then there's the things that we see, if you'll forgive the pun, see from a distance. Space exploration, some of the really large telescopes, things that we run into in the hospital, things that we read about, or for those of you who might end up serving in the armed services, might get a chance to see how optics is used in defense. But in manufacturing especially, how optics and cameras and lasers are used in machine vision and in manufacturing processes, and so forth. But now we have to go back to thinking about the nature of light, because when we study light, we have to sort of build it up from basic concepts. We start out with the idea of light as a ray. And we figure out how light changes direction as it passes through materials. We figure out how to model it, and this is just an example of a simple computer model drawn in 3D. But then sometimes tracing rays through lenses isn't enough. Sometimes you have to figure out, you have to break light into its spectral components, its colors, if you like. And sometimes you have to understand how light will go through multiple components, such as prisms, and how that works, for example, even in a laser cavity. But just understanding light as a wave isn't enough. Sometimes you need to understand the polarization of light. You can think of that as sort of the direction of wiggle of the wave of light. And this is just an illustration. If the light is traveling into or out of the screen, light could wiggle in what we might consider a horizontal direction or a vertical direction. We call those directions polarization. As I said, the study of light goes way back. It goes back to the ancient Greeks, but it also goes back to the Arabs. And some of you may not be aware of what there were wonderful mathematicians among the different Arab groups, depending on whether you're using the Christian or Muslim calendars here, who discovered some of the basic mathematical rules of how light propagates. And then there are a tremendous number of names that you will learn about as you go into modern optics, which early on was very, very closely tied to the development of modern physics and even mathematics. So you may recognize the name of Descartes from mathematics, Newton, of course, from physics, but he wrote an impressive tome on optics, Galileo, the first at least verified telescope, Fresnel, the first basic understandings of light as a wave, and then Maxwell and Einstein, who contributed to our modern understanding of electromagnetics, and Einstein, our modern understanding of quantum optics. But all of us, if you think back to it, or perhaps even before you can remember, our first introduction to optics was the eye. And so we open our eyes, we see light, and we don't always appreciate how long people took to understand exactly what light was, because they knew they could see it with their eye. And for a long time, people thought that perhaps light was something that was coming out of your eye and kind of illuminating the world behind you. And of course, the world around you. And of course, we know that must be true, because if you close your eyes, you can't see anything. So it must be blocking whatever light is coming out. And of course, you're all versed in modern science, and so you know that's not the case. And they did a lot of experiments to figure out and verify and say, light is something coming from the outside into our eyes, and it's being sensed back and going through an imaging device. And somebody like Newton was convinced that light, as it was coming in, said, well, it's coming in as a stream of particles. That just makes sense. And he had models to work out how light was a stream of particles. But then Fresnel and Young came along, and they said, no, they did experiments to verify that, in fact, light was a wave. And so even in our understanding of vision and basic imaging systems, there was still a lot of debate on this question right into the 20th century. Now, we can do a little bit of exercise in vision, since we all associate light with vision. And so this is something, if you're watching the recording, you have to do at home. If you have a dark background, it helps, but it still works. What you have to do is you have to focus your eye on the black star in the center and keep your eye very, very steady. Focus it for a second, 3 seconds, maybe focus it for 15 seconds or so. And then keep it focused, and then we're gonna switch over. You're gonna have to tell me what we see. You look away and then look back. And if you saw what I saw, what your eyes saw initially, then we'll go back and do it again, because if you didn't see it right away, sometimes it takes a second chance. Look at the black dot or the black star. Keep your eyes trained on it, keep your eyes trained on it. And now when I switch it, you should, just for a few seconds, perhaps just a second, see a colored image. Then if you look away and look back, you realize, and if you blink, you realize it's a monochrome image. What you're seeing there is the persistence of the color effect in your eye. Now, this is an optical illusion. It's something that you can find on the internet. It's not original to me or to the Institute of Optics, but we do have people who are working on just fantastic research on vision and how the photoreceptors in your eye work. Because one of the things that we don't always appreciate when we see optical illusions like we just saw is that for generations, people have understood that these sort of optical illusions exist and how to work with them and so forth. It's been in only recent years, and it's really been headquartered in many ways in Rochester, the understanding of what's happening inside the individual sensors of the eye. And this is Professor Jennifer Hunter, just one of a number of professors we have at the Institute of Optics, but who are also over in the Medical Center at the Center for Visual Science and Ophthalmology, who are using new laser-based devices and optical imaging devices to better understand the photoreceptors in the back of our eye, both for the basic knowledge, but also ultimately for better ways to be able to diagnose and treat eye diseases. Many of you are aware of the importance of optics and energy. We have a tremendous amount of light-based energy hitting our planet every day, and we see solar energy around us. The technology you see on the upper left is, of course, a solar panel. It's made of silicon. It absorbs light. And one of the things that I teach my students in our introductory optics course, Optics 101, is a lot about how solar panels work, how to do basic calculations of efficiency based on solar panels and so forth. But what you also have to appreciate, if you just look at the world around us, is that there's a lot of sort of natural solar cells just sitting there out in the world. And so this is a picture by my daughter's house in Vermont. And every leaf that we look at is a little solar panel that's pointing at the sun. It's absorbing solar energy. And instead of converting the solar energy into the electricity like a solar panel does, what it's doing in a leaf or a flower or any other plant is it's absorbing the sunlight and it's converting that and storing it into chemical energy. So this illustrates a couple of things that's important for all prospective engineering students to understand. And I hope you'll learn to appreciate this as you go on to your studies. And that is, when you start getting into applications like energy, like lasers, like almost anything else in science and engineering, we don't exist on our own. Optics people solve part of the problem of solar energy, but there's a tremendous amount of mechanical engineering, there's a tremendous amount of electrical engineering, and there's increasing amount of chemical engineering that goes into the design and optimization of solar panels. And if you think about a leaf as a solar panel, it's like the original chemical engineering. The photons come in, they get absorbed, and the chemical engineers do all the work from there on out. So everybody knows that we really like our colleagues in the other disciplines, because if there was only light in the world, we wouldn't be able to do very much with it. So how do we understand light? One of the things we take light apart is we separate it out into colors, but colors are only, of course, the colors that we see. And if you go beyond the blue, and we quantify that often in wavelength, sometimes in frequency of the electromagnetic wave. If you go to very, very short wavelengths, and these are numbers based in centimeters, you're going to the ultraviolet and eventually to the X-ray, and eventually, if you go all the way over to the left, over to the gamma ray region of the spectrum. These are all electromagnetic waves. If you go the other way, beyond the red, you're going to the infrared region of the spectrum. And that infrared region of the spectrum will carry you out to regions where we do data communications. If you go further out, we do regions of the spectrum where we do atmospheric sensing. It turns out there's special regions of the infrared here that can see through smoke and fog and clouds and so forth. There's a region of the spectrum that we use for night vision. And then if you go all the way over, then what you'll find is that there's a region of the spectrum that is even good for security scanning, the so-called terahertz region of the spectrum. So now I want to dig in a couple of examples of some interesting things about light that you may or may not know about. And first, we're going to talk about the light you see and what we see around us. And so one of the things that we think about a lot in optics is, okay, where does the light come from? If we look at something, and this was from a Walmart parking lot, if we look up at the clouds and we say, okay, I'm pretty sure the cloud is not emitting its own light. Where is that light coming from? And of course, we know from context that light is coming from the sun, but we also know that the light from the sun, if we look at it directly, is not that orangish color. So something must be happening to the sun in the process of either getting to the cloud or bouncing off the cloud. And so we have to start studying light scattering. We look at the blue sky. We say, well, that blue color is also coming from the sun, but that's a very different color than the orange color coming from the cloud. But that also is coming from light scattering. And so we say, it turns out if you were to take a Polaroid filter, a polarizing filter, you would see the polarizing filter has a different effect on the sky than it does on the clouds. Now, if you look in the lower part of the picture, you see something that is manifestly not sunlight. It's a synthetic light. It's a man-made light that's used just to light up the parking lot. And of course, those go from the older designs of sodium lights and fluorescent lights to some of the much more modern, efficient LED lights. The study of optics includes all of that. You look at natural phenomena like rainbows, and we try to understand how does that natural phenomenon occur. And you use that using the tools of geometrical optics, but also increasingly with the tools of wave optics. If you look closely at just a puddle of water out on one of our, the pavement out by our laser lab, and this was after a rain while I was out on a walk, and you look carefully with the sun bouncing off it, you can see all kinds of different colors. And those colors are being produced not by pigments, not by absorption, but by an interference effect of the oil film at the surface. If you look at a scene like this, you're seeing a mixture of colors that are associated with absorption, the pigments in the grass and the leaves, the pigment in the blue ball, but there are also colors in nature that appear because of light scattering. And sometimes, even in something as simple as a butterfly, what you see is colors that are forming from the tiny, tiny nanostructures. There's no pigments there necessarily that absorb the light, but you have little tiny nanostructures that control which colors get scattered back and which colors come in and get absorbed. We study the bending of light a lot, and you can see the bending of light, but even from clear materials, even when light hits a material, a certain amount of light will reflect off that material. And so one of the things we try to understand in optics is, okay, how does that work? How does it work in terms of direction? How does it work in terms of the color dependence of that reflection? And we can look out at nature, and we can take something as clear as water, and we look at it at a distance, and we know that water will reflect in a very mirror-like fashion. And then what we do is we build giant lenses of many, many elements. And this is an old lens that we have that was cut in half for a display. This is actually a very small lens when it comes to making lenses for photolithography. This is a lens that was built by Trapel Corporation to manufacture computer chips way back in the mid-90s. You can learn some things about space telescopes from even ordinary scenes. So this is a picture of a reflection off a building down in Sydney, Australia, but you can find this in almost any city. And here we're looking at the reflection of a neighboring building. And what you look at when you zoom in on this reflection of the other building, you see that the smallest changes of angle in the windows make a huge impact on the quality of that image. And one of the things that we study a lot in optics is how to make and measure surfaces so that they have very precise surface slopes. But the other thing that people, both at the Institute of Optics as well as our graduates, have been working on is space telescopes like the James Webb Space Telescope that have many elements just like these windows, but those elements have to be so precisely aligned so that each element brings the image together in a perfectly and absolutely aligned way. When we bounce light off mirrors, we see a magnification effect. Okay, and that magnification effect has to do with as the light bounces off a mirror, the law of reflection will send the light at various different angles depending on the slope of that mirror. What we might be less aware of is that you can take surfaces that are curved in one direction, but not necessarily curved in the other. It's called anamorphic imaging, and you can control light distributions that way. Sometimes you can influence the shape of laser beams, but more and more these days, surface shapes like this are being used in things like virtual reality, augmented reality, and new kinds of optical systems that are built around surfaces that aren't necessarily spherical. If you've ever been underneath the water in a swimming pool and looked up toward the surface, what you'll see is a very mirror-like effect as you look at an angle, and this is called total internal reflection. When light comes beyond a certain angle, inside a surface of higher refractive index, think about a surface that might be more dense, still transparent. It could be water or it could be glass. And you're looking from inside the water, there's a certain angle beyond which the light will totally reflect. And you end up with a mirror, a perfect mirror at that surface if it's flat. And this is sort of a bumpy surface looking from inside one of these aquariums where you're surrounded by water. But here's an example of looking through the wall of an aquarium where the surface of the water is very, very still. And here we're looking at just a back rock wall. And if you look very carefully, all the features up here are perfectly duplicated there. We're looking at a near perfect mirror. Now, what are you going to do with this apart from take cool pictures at museums? Well, if you take a laser beam, and here we have just a green laser beam, and it's going into just something simple like a piece of plastic, what you find is when light is at a steep angle, light will be trapped inside and even be able to be guided around corners. And this becomes the origin of a kind of light guide or waveguide if it's small enough, and it becomes the basis for optical fiber communications. Optical fiber communications, which of course started way back in the 70s and 80s and sort of started to take hold in the 90s, has now become the mainstay of communications inside data centers. Why is that important? It's because every time you go to Facebook or you use Google Drive or use anything on the cloud, your information is being stored somewhere in the world in a data center. And you've got servers and storage facilities like you see here that are taking huge amounts of energy to get the data onto and off of the storage devices. And so increasingly people are turning to optics to be able to take the signals, sometimes the very high-speed signals, increase the capacity so that we can get more and more gigabytes per second over the channels. And one of the ways we do this is we start combining optical wavelengths on a single fiber and then separate them out at the other end. You could do this with a prism. You could even do this with a raindrop. But more and more, what we do is we do it with what we call diffraction gratings, where light hits a grating and the scattering of the light goes off in many different directions, but each wavelength will go off in its own specific direction and allows you to combine and separate light. This effect is there with certain animals, like for example, the wings on certain, especially waterfowl, but you can also fabricate this into semiconductor devices. This is what it looks like in a schematic way. If you take a bunch of wavelengths and you combine them on a single fiber, MUX just stands for multiplexer. DMUX stands for demultiplexer, or the separation of the wavelengths. And we're able to, using technology, to combine and separate these wavelengths very efficiently to get huge amounts of data capacity at very low energies. But a lot of times these systems look very big as we start putting them together. And so what engineers and scientists are working on more and more are waveguide-based devices that will separate out these channels, these different wavelengths, and make the optical equivalent of little tiny semiconductor integrated circuits. And one of the things that we do in Rochester at the Institute of Optics, in a consortium with many other universities and industries, is figure out new ways to trap light on structures. These are pictures of silicon waveguides made at an organization that I work with called AIM Photonics, where the size of these waveguides is only a couple of hundred nanometers in size, less than a micron, so this would be less than 1/100th of the diameter of your hair. Little tiny waveguides. This is one made of silicon nitride. And one of the things I do in my labs is we've built a special near-infrared microscope to illustrate how light couples in from a fiber to one of these little tiny waveguides, how light travels around, and how it interacts, how it couples to different components. One of the things that we like to do, or that at least some people like to do, a lot of our faculty and graduate students, is to try to go faster and faster. Not literally in terms of human speed tests, but how fast can you measure things? How fast can you make a light pulse to be able to measure very, very short things? So if we were to blink our eyes or look at the speed at which we can spot things moving, that's about 5/100ths of a second. If we go to a high-speed shutter, let's call it a millisecond. Sometimes it's a little bit faster if it's a liquid crystal shutter. And this is a little bit dated. Now it's faster than this, depending on how much money you put into your internet connection. But it used to be that you'd have one bit of information about every microsecond coming into your home. Now it's 10 or maybe 100 times that, depending on your data rate. How fast is a molecular vibration? That's around 10 to the minus 12 seconds, so 1/1,000,000th of 1/1,000,000th of a second. How long does it take an electron to oscillate when it's trapped on an atom? So that's 10 to the minus 14 seconds. That would be about 10 femtoseconds, or less. How fast does a wavelength, a period of vibration of green light take? Well, that takes about 1.8 times 10 to the minus 15 seconds. And people have made visible laser pulses down to a few femtoseconds, and they've made ultraviolet laser pulses even less than a femtosecond. What might you do with that? Well, there's a lot of things you could do with it. You can, if you go down to the National Institute of Standards, you can do more ultra-precise time and frequency measurements. You can use laser machining or modification of materials. You can do faster communications, lots of things. One of the things Donna Strickland did way back when she was a graduate student at the Institute of Optics is she, with her advisor, figured out a way to stretch optical pulses, amplify them, and then squeeze them back together again in order to get 10 and even 100 times the power out of a laser pulse. So those of you who are dreaming of wonderful things, just think about the fact that Donna Strickland, even while she was a student here at the Institute, was able to do work that eventually, it took a while, but eventually it won her the 2018 Nobel Prize. But there are other things that you can do. This is recent work from one of my colleagues, a faculty member at the Institute of Optics, Chun-Li Guo. And what they've been doing is they've been taking femtosecond pulses and using it to treat or modify the surface of optical materials. In this case, a simple metal or semiconductor wafer. And they've been able to modify the chemical and physical properties of that so that in this case, it becomes a special material that repels water. Now, normally when a drop of water falls on material, it's just going to go splat. Watch carefully what happens when this drop of water falls on the material. And if you're wondering how this might be useful, just think about situations, whether they're expensive situations or just ordinary situations, where you might want to have devices or things that just don't soak water, don't repel water. Any of you that are interested in other technology, go do a web search for Professor Guo, G-U-O, and look for the term floating metal, and you'll see some other fantastic videos. One of the things that we love to do in optics is we like to see how small we can go. And one of the things that you can do through fluorescence is you can use optics to actually see or locate individual molecules. And we do this through fluorescence. Many of you are aware, if you just shine an ultraviolet light, a black light on various different materials, you get all kinds of beautiful fluorescent colors. Those fluorescent colors are the properties of the molecules that make up those materials. And what we were able to do a number of years ago was work with one of my colleagues here to do some special polarization-based measurements on single molecules and look at single molecule fluorescence. So we're coming in with blue laser. The molecules are sitting down in the microscope on a microscope slide, and now you're scanning through and you're seeing the individual molecules. Well, one of the things that we did with that was we made use of some of the research that I've been doing for many years in my work, and that is some special work on polarization. And one of the things that we use is stress engineered optical elements. So if you look at just an ordinary clear item under stress, the stress birefringence, the stress effects in polarization, are going to produce some very, very vivid colors, even in a material like this. Many of us have seen demonstrations like this, and if you come to the Institute, I'd love to show you this in person. But this is just ordinary plastic picnic ware viewed through polarizers. What we do is we put stress on an ordinary window in order to produce a polarization effect that actually produces a kind of vortex, an optical vortex, in the little donut region there. Well, you may be acquainted with what a vortex is. You know, if you go out and look on the weather maps and see a circulating a map like this or a picture like this from of a hurricane, you know that there's swirling winds going around the eye. You can also view this with swirling water in a bathtub and so forth. These vortex effects are everywhere in nature, where there are vortex effects in optics as well, where the energy swirls around a point, but the center is very, very quiet. And in optics, we can produce beams that have a vortex in the center where the energy swirls around that center, but never actually passes through the center. And one of the things we can further do that my group studied was how to create polarized light that's arranged in either a spoke-like or in what we call an azimuthal or tangential direction. And we started studying how light like this behaves with these single molecules. And it turns out single molecules behave a lot like antennas. If you take a polarized wave and you have a linear molecule, if the molecule is aligned with the wave, it will absorb the light. But if it's not aligned with the wave, it won't absorb the light. And so what we were able to do was create a focus that had all kinds of different polarizations in their focus, including some polarizations that were along the axis and some polarizations that were laying on their side. And then we put this into the microscope. And what we found, and on the lower left is the ordinary microscope image. On the upper left is what you see when you modify this microscope. And what you're seeing is not only the molecule location, but you're seeing its orientation in 3 dimensions. Here's a molecule that's laying on its side, kind of. Here's one that's kind of tipped up. Another one that's tipped up. Here's one that's standing on its head. And by analyzing these shapes, you can actually figure out the molecular orientation. And this work was done quite a while ago, but it hasn't stopped. I continue to work with a group in Marseille, France, and some of my colleagues there on more advanced work in there. So we just want to wrap up by telling you, just recapping for you where you can find imaging applications. It's everywhere. It's thermal imaging, all the way down to traffic control, and now, autonomous vehicles. A few things about opportunities for undergraduates, particularly summer opportunities, but some of these are also available during the year. There's faculty research labs. There's in the Med Center, there's the Center for Visual Science. We have the Laboratory for Laser Energetics. We have the Strong Medical Center that does other work as well. There's a lot of local optics companies. So a lot of students are able to stay here in optics and get jobs in local industry. But sometimes you might have heard of companies called Apple and Google and Microsoft. They are members of our industrial associates. And so a lot of companies in their internships will get a chance to go to one of these companies, go to NASA, go to Ball Aerospace, companies that are involved with defense, and even in some cases, some of the national labs. Here's just a snapshot of an optics curriculum. It's built on foundational courses that are common to all the engineering disciplines. Then we have courses that focus on ray-based or wave-based properties of light. And we also have we have laboratory courses that go along with each one of those areas. We have courses where you'll learn particular skills like lens design. There's other courses where you learn a broad spectrum of knowledge in optics. You'll take courses from the math department, of course, but then we have sort of a capstone course that you'll take in the optical applications of math methods, quantum optics, and so forth. And then you end that all off with either a team-based design, if you're an optical engineering major, or a capstone project. Finally, just to give a little bit of recent study, optics graduates really like their job. This is the latest numbers from just about a year ago, maybe less than a year ago. 95% of us really like our jobs. Now, I have to say this was pre-COVID, but I think we still like it. Pretty good medium income, and you'll find this is consistent with many of the other engineering disciplines. And our students, they come out of the Institute of Optics with a degree that's known throughout the world, and especially among the technology companies within the United States. So students that are optics students really join not just an amorphous group of alumni, but really they join what we like to think of as the optics family of alumni that are throughout the area. So this is just some summary. I know we have some time, I think, for questions, if there are questions in the chat, or if those of you who are listening to a recording on this, don't hesitate to send your questions to Nick, or also to get in touch with Dustin Newman if you have other questions as well.
Professor, what do you think the biggest misconception for first-year students is about optics and optical engineering?
So a lot of times the misconception coming in is, that when they first see the word optics, sometimes people associate it with eyeglasses, ophthalmology, and so forth in medicine. It's much more than just, in fact, optometry is its own separate discipline. It's a medical discipline. We are not a school of optometry. We're a school of optics and optical engineering. And so I think what a lot of students don't realize, the breadth of optics, that it goes all the way from medicine to consumer technology and so forth. And I think one reason for that is that sometimes optics is hidden. You know, we don't always think about all the optical components that go inside a cell phone. There's the display, there's who knows how many cameras on here, there's the LED light that you like to turn on and so forth. Those are just the obvious things. Then there are the things that go into the manufacturing, the design of the cell phone, the manufacture of the integrated circuits, the machine vision systems that you would use to inspect the components. You cannot place a transistor or a component onto a circuit board without optics. There are vision systems that are relied on to do that.
Another question we have is, hi, Professor Brown, can you talk a little bit about the intersections of optics and ECE?
And which?
Optics and electrical and computer engineering.
Quick suggestion, could you unshare your screen so we can see your face maybe?
Oh, yeah.
Oh, absolutely. Let me... Okay, this is better.
So they're asking about the optics and electrical and computer engineering.
Okay, yeah, so that's a great question, and there's parallels to this question that could also apply to things like mechanical engineering and so forth. So the interface between optics and electrical engineering happens sometimes in the high-speed electronics, because in order to get an optical signal, it usually, say a data signal, it usually has to start out as an electronic signal. And so somebody has to work on the electronic side of the circuit and design that circuit before the signal finds its way onto the light. When it comes to the detection and sensing end of things, the interior of an image sensor, a lot of that is electrical engineering. That goes into the design of different devices and the circuits that you would design, for example, for image compression, for handling some of the various image information, for doing high-speed detection of data signals and so forth. There's also on the computer engineering side, because we're talking about ECE, electrical and computer engineering, a lot of need in optics for people to come up with new algorithms. And sometimes once you figure out how to calculate, you come up with a new method for doing, say, image processing or measurement on an image. Sometimes now you want to actually put that into either firmware or software code in what's sometimes called an embedded system. And to do that kind of engineering, a lot of times you would want somebody from electrical and computer engineering. There are similar things that are true in other disciplines. Mechanical engineering, we wouldn't be able to design, manufacture, polish optics, or even fully understand how a laser interacts with optical materials if we didn't have people in mechanical engineering that were working on solving those sorts of problems.
Just before I forget, Laura, did you want to say a few things from?
Yeah, I'd be happy to. Thank you. Yeah, so I'm Laura Jones. I'm one of the career advisors at the Green Center, and optics is really cool. It's a challenging major. I've worked with many students who are optics majors, and I think figuring out what to do with it is probably nearly as challenging because there's so many options, as Professor Brown described. So at the Green Center, you can come work with us and figure out, what do you want to do? What do you want to try out? We can help connect you with internships and research opportunities. Of course, you're going to talk with your faculty about research opportunities. We can help you network with alumni, and Professor Brown referenced how close-knit the alumni community is in the Institute of Optics. I found that as well. And so also the Industrial Associates gives you great opportunities to develop those networking skills and develop your alumni network from early on. So you really can't go wrong with an optics major, honestly. Our website is rochester.edu/career center. Check us out. And thanks, I really appreciate the opportunity to pipe in here.
A lot of people think Career Center means you go in there your senior year when you're looking for a job, but there's a lot there for freshmen, even for prospective students. You're thinking about what you might major in. It's a really good resource for students at all levels. So I'd encourage students to sign in there and take a look. Even if you're the prospective student, please take a look at the Green Center.
Yeah, we'd be happy to speak with anyone.
Do you have any more questions for Professor Brown? You can contact either Professor Brown. We're going to put his contact information alongside when we post the video. If you're interested and you're watching this and getting a prize, you can email me at nicholas.valentino@rochester.edu. I will put that as well. Dr. Brown, thank you so much for coming and doing this for us and being able to explain the world of optics. And hopefully we'll have students who will be able to follow up with this. As we're hoping these presentations are the start for students to find something for which they're interested. So thank you for coming and doing this.
Thank you.
All right, that is all we have for today. We'll be back on Wednesday for electrical and computer engineering. Thank you all for watching, and we'll see you soon.